Atomic theory is something that many students find either daunting or worse, boring. Many of these bored students do not realize how important atomic structure really is. Knowing the structure and components of an atom is what allows us to create newer and greater technologies, like nuclear power and hydrogen fuel cells. To understand modern atomic theory, it is important to know how it has evolved through history. Surprisingly or not, the first people to think about the nature of matter were the Greeks. The Greek method for conducting science was usually philosophy-based. By that I mean for Greek scientists, an experiment meant thinking about an idea without actually physically testing these ideas. In this manner, they were able to explore and develop ideas that were far more advanced than the technology that was available to them at the time. In 460 BCE, a Greek philosopher named Democritus was using a piece of chalk when he began to think about what would happen if he broke the piece in half, then one of the halves in half, and then one of those halves in half as well, and repeating this process over and over. The end goal was to try and determine if there was ever a piece of chalk so small that it was indivisible. He called this theory atomos, which means uncuttable, and is the first theory about the atom. Unfortunately, Democritus' ideas about atomic theory did not resonate with the other Greek philosophers of the time, including the infamous Aristotle. Due to the fame and respect for Aristotle, most Greeks followed Aristotle's lead and dismissed the idea of atomos as worthless. This lack of hard scientific thought about the nature of matter continued for the next 2,000 years into the beginning of the 19th century. In 1808, English chemist John Dalton published his book, A New System of Chemical Philosophy. In this book, he writes out his ideas on chemical theory, which are now centered around what we now call the atom. Dalton's atomic theory had 5 main points, which are the basis for modern chemistry and are still used even today. These ideas were revolutionary in chemistry and generated a great deal of interest in this new field. In 1897, another English scientist named J.J. Thomson published his discovery of the first subatomic particle, the electron. Thomson discovered the electron through experiments conducted with cathode ray tubes, which nearly 100 years later were used as the first computer monitors. For the first time, scientists had uncovered hard evidence linked to the structure of the atom. Thomson's discovery of these new subatomic particles led him to develop the first detailed model of the atom. Thomson's model depicted negatively charged electrons floating in a lump of positive matter. This model was dubbed the plum pudding model, due to its resemblance of electrons to raisins, which would be floating in a bowl of plum pudding, as was a famous dessert at the time. In 1899, a New Zealand-born chemist and physicist named Ernest Rutherford discovered 2 new types of radiation, both alpha and beta rays, which he found through his study of thorium and uranium, respectively. As Rutherford worked with radioactive materials, he discovered the third most common type of radiation, known as gamma radiation. It is Rutherford's work with radioactive emission in 1909 which inspired him to use radiation to try and explore the nature of the atom. In 1911, Rutherford performed his famous gold foil experiment, where he shot alpha particles at a sheet of gold foil to probe the atom. He expected to see the particles pass right through, which would be indicative of the plum pudding model. Instead, Rutherford observed most of the rays passing directly through, but a small percentage that were deflected at very high angles, which would indicate an organized structure and a mass in the middle. By examining his data, Rutherford was able to construct a revolutionary new model for the atom. In Rutherford's model of the atom, he depicted a positive core of particles, which he dubbed protons, with negatively charged electrons orbiting the core, or nucleus. Rutherford equated the behavior of the electrons to the planet's orbit around the sun, and called the path that the electrons take orbitals. Around the same time that Rutherford was pioneering his work, a Dutch physicist named Niels Bohr began to study the experimental data from Rutherford's experiments, and he set out to interpret this data, how it would affect the structure of the atom. Bohr concluded from the data that electrons do not spiral towards the nucleus, but instead had distinct orbits which existed at defined energy levels. In 1912, after his research into energy levels of an atom, Niels Bohr developed his own model of the atom. In this model, which is very similar to the Rutherford model, there is essentially a nucleus with distinct orbitals, but the Bohr model was much more focused on the idea of categorized and distinct energy levels, as well as photon emission. In the 1920s, the Bohr model came under criticism after experimental data showed it was not true for all cases of the atom. Bohr and another German physicist, Arnold Sommerfeld, expanded the Bohr model to explain these variations. In this new model, electrons not only travel in certain orbits, but these orbits can have different shapes, which are then distorted by magnetic fields. Just by looking at the Rutherford and Bohr models, it is plain to see that the two share many similar characteristics. In fact, Bohr and Rutherford were colleagues, as well as friends, who were looking at the same atoms, but were trying to answer different questions about these atoms. Rutherford was more concerned with structure, while Bohr was more concerned with energy levels and how these energy levels affected reactivity. In 1924, an Austrian scientist named Wolfgang Pauli predicted that an electron should in fact spin while it orbits the nucleus, much the way the Earth spins as it rotates around the Sun. This led him to develop a theory in which no 2 electrons could have the same spin or be in the same orbital. This became known as the Pauli exclusion principle and is still used in modern chemistry today. In 1926, an Austrian physicist, Erwin Schrödinger, decided to try and form a model for the atom which incorporates the idea of particles as waves. This was a radical idea for the time because when the atom is viewed as part of the wave function, it behaves in a way that we did not think possible. It is hard to prove or disprove this theory because the behavior of the atom is not comparable to anything we've studied before. In 1927, Werner Heisenberg, a German scientist, formulated an idea that no experiment is able to measure both the position and momentum of a quantum particle simultaneously. This theory was supported by experimental data. This theory went on to become known as the Heisenberg uncertainty principle and is the basis for most of modern quantum physics. In 1932, a former student of Rutherford's, James Chadwick, discovered a new subatomic particle which has mass but no charge and exists as part of the atomic nucleus. This particle was named the neutron due to its neutral charge, and forced revisions to be made to all the atomic models at the time, much in the way that their nucleus is formed. Based on the discovery of the neutron and the theoretical framework set up by Heisenberg's uncertainty principle, the electron cloud model has been developed. This model is in its most simple form a probability density, where you are most likely to locate an electron. Every dot in this model is a probability for where an electron might exist, so the denser the area, the higher the probability that an electron is inhabiting it. With newer and better technologies, we are able to actually get closer to painting a literal picture of the atom. For example, IBM's new microscope is able to see the bonds between atoms. What you are seeing on the screen is a colored representation of vibrations that were detected by IBM's new technology. This is only the beginning of atomic exploration, but is opening up new boundaries to where we can